infinity and then converted everything in terms of Reynolds number and Prandtl number to get Z optimum. Z optimum is again when you equate QF small and QF large. So this is where we stopped in the last class, that is on Monday. Now we'll do something else again, speaking with fin arrays. So this is another discussion of fin arrays. Now in this case, we want to find the beta for the array. So there was a beta that we are familiar with. So beta is MB. And what we did was for a particular fin, for a single fin, we said that if we prescribe this area, which is B multiplied by T, that is profile area, AP equal to B multiplied by T, if we prescribe that, then the heat transfer is maximized when beta is a particular number. So we did dQf dt equal to 0. From that, we arrived at beta equal to 1.4192. So this is just a recapitulation of what we had done previously, but that was for a single fin. What I'm going to do now is we'll go through this beta, a derivation of beta for a fin array. So what sort of beta value for the fin array will give the maximum possible heat transfer? So this is again not very difficult. So QSF is the heat transfer for single fin, QSF. That is root HPKC theta B tan hyperbolic MB. Yeah. So what is this for? This is single fin general heat transfer expression, isn't it? QF. This is for which boundary condition? Remember from your undergraduate days that there are 4 conditions for fin. And the heat transfer expression, we have a general expression. Then for those 4 boundary conditions, we have separate expressions for QF, right? Which one is this for? Finite length. Yeah, so not much heat transfer from the tip of the fin. So that's the expression. Or you can say adiabatic tip or insulated tip, whatever. So that's the heat transfer expression. Now, we'll try to get an expression for Q total in this case. So the total heat transfer that takes place in the fin array. Now, recognize that the heat transfer in this case will take place through the fins, but also between the fins at the prime surface. So what is the prime surface? Prime surface is actually this thing. Without fins, whatever surface you get, that is the prime surface. And I'm saying that there will be heat transfer through these fins, but there will be also heat transfer through this interfin area. Interfin area. Now let's look at the heat transfer through the fin. We're writing S for single. Now AP equal to BT by definition. This is profile area. AC is LT, which is the cross-sectional area. Now P is approximately 2L when the thickness is small compared to length, right? And beta equal to MB by definition. So m is square root of hp by kac, and m can be shown to be, using these, shown to be 2h by kt to the power half. And then if we use expression for p and expression for ac here, then we also get an expression for qsf. Just take 30 seconds to look at this and tell me whether this is all right or not. QSF expression. These are not many expressions, so you can just write those, then that way you'll remember better. If you just stare at the screen, it's not going to help you so much. Okay. Don't have to write everything on the screen, as I have said before. In fact, don't even have to read everything on the screen. Just write a few things so that you can, these will act as clues when you go home and take a look at the note. Then you'll remember, okay, these topics were covered, these equations were covered, things like that. Last, whatever steps are missing, do those at home. All right, so QSF is all right here? QSF is fine? You're not saying anything. What is AP by B? It's just T. So this should be all right, even though you're not saying anything, no response. Okay. Now, so there is the saying, Maunam Sammati Lakshanam. Okay, so I have to assume that if you keep quiet. Now, as I said, heat transfer from the interfin area also has to be taken into account, because for the entire fin array, we're trying to get a beta, right? So QW is HW LZ theta B. Now, LZ is, this is Z, this is L, so LZ is that interfin area between fins, right? HW is the heat transfer coefficient at the wall. And theta B, as we know, is theta is T minus T infinity, so theta B is TB minus T infinity. Right, and N is the number of fins. So if N is the number of fins, we can write this for QW over L. See, this is QW, this is L. So QW over L is HW theta B multiplied by this thing. So what is this? It's actually shown here. W by N minus T is your Z. And then the T is AP over B. T is AP over B. Okay, so we get this, and then Q total is number of fin, Q total by L is number of fins multiplied by, this is what? First term. What is the first? This is the heat transfer through single fin, right? And this is the heat transfer through that interfin area, right? But there are, I mean, if you think about the fin, okay, to think about the fin and the adjoining interfin area, then you get this much, and we have n of such things, such units, right? So that's why it has to be multiplied by n. Okay, so I also have this photo. I've attached it here. I just thought that it is kind of like helpful to keep this picture in mind. So this, in our labs, in many of our labs, you have such seating arrangements for PG students and basically PhD scholars. Right? So these are cubicles, and then these are partitions and all that. So if you neglect what happens here, then this picture is similar to this, right? So if you remember this, then it's easier to remember the vertical fin arrangement, isn't it? So as if these are like fins through which heat transfer is taking place, and this part is the prime area, the interfin area basically. Okay. Nowadays in corporate offices, I'm told that this design is not exactly a very good design. There are other kinds of designs, but we are not going into those. This is just a helpful photo that can assist you in remembering this kind of a geometry. All right, so we got Q total. Now what should we do? We can try to get the minimum here. Try to get the maximum here by doing dq total dB equal to 0. This is in terms of B. It could have been written in terms of T also, but this is written in terms of B. So we'll do dq total dB equal to 0. And if you do that, then you get this sort of an expression. So this is similar to what we got for a single fin sometime back. In fact, if you set HW equal to 0, then this is like just a single fin without this consideration of the interfin area. Then this will just turn out to be same as what we got in our single fin analysis. So you imagine setting HW equal to 0. Okay. Then this thing should give you, what did we get previously? We got 6 beta equal to sine hyperbolic. We got something, right, for single fin. What was it? Two beta. Yeah. So 6 beta equal to sine hyperbolic 2 beta. Remember that I had plotted this and had also plotted this. So where these two curves intersected, that was the solution. Right? Now, the expression that we have here, this one, if we set HW equal to 0, then you get this expression which will actually give you 6 beta equal to sine hyperbolic 2 beta. Okay, just a matter of simplification from here. And this gives beta equal to 1.4192 again, obviously. Correct? Same equation. So HW equal to 0 means there is no heat transfer from the interfin area. So it's like all single fins. Correct? If HW is non-zero, then the interfin area makes sense, isn't it? In actual case, obviously HW will make sense. Now we can, in fact, from here, we can try to get various solutions of beta. How? Let's say we know something about, we say something about HW, 2HWB over K. So this 2HWB over K, we can take it to be some value. We take one value, then solve that equation. Take some other value, then solve this equation. We keep doing that. So we can take some number like maybe 0.2 or 1 or 1.5, whatever, some number. If you get some number here, then this equation can be solved to get beta. Okay, how do we solve this? There are root finding methods. You learned about root finding methods? These sort of equation, non-linear equation root finding. So there are, what are some of the methods? You did some numerical methods course? Yeah, so somebody gives you that just that equation. Right hand side just some number. How do you solve this to get beta? Just tell me the name of some method. Yeah, yeah. So you can have some method like that to get solutions. So then we get various beta values for various values of the right hand side. And then we can plot this beta values that we obtained on the y-axis, and we can have HW by k on the x-axis. Then we can generate a curve, right? It so happens that the curve is actually can be approximated by a linear relation. You understood what I'm saying, right? So I said that maybe you can do this beta and HWB over k. You choose a value of HWB over k, you get a value of beta, right? Choose another value of HWB over k, you get another value of beta, like that. If you get all these solutions, then you plot, then you can see that we'll get this sort of a linear relationship approximately. So you can curve fit the data and get approximately a linear relationship. Okay, and this gives you that linear relationship will give you something like this. Maybe what we can do for tomorrow's class, tomorrow's design class, is that you can try to generate this. Okay, so maybe you can revise your Newton-Raphson method or some other method to get roots, plot, and get this line. In class, you get 2 hours, so in those 2 hours, it should be possible. Now, from this, we can see various values of beta array. Now, the beta that we are getting, this is for an array. So we say B equal to 3 centimeter, K equal to 175 watt per meter Kelvin, which is aluminium, H equal to 6 watt per meter squared Kelvin. These are values that I am assuming. So H equal to 6 watt per meter squared Kelvin, reasonable, because often we use fins when there is natural convection, and H is in fact small, correct? So in this room, H is not high, even the air is hardly moving. There's a little bit of natural convection draft, which you can't even feel properly, right? There's hardly any H. So something like that's aluminium, this is 175, could have been taken as 200 also, but this is temperature dependent. And this is some value of B which is taken, and that will give you, from here, that will give you 1.42. If you vary H from 6 to 100, keeping other things the same, then you get 1.438. And if you go back and keep H as 6 watt per meter squared Kelvin, the first value, then you change the material. Let's say you choose cast iron. Cast iron is 30 watt per meter Kelvin, and B equal to 20 centimeter. Then also beta array is 1.464. So we can study this, we can have various combinations, and we'll end up seeing that the beta is not very different from 1.42. It's in the third case, it's slightly different, but the change is also in the second decimal place. All right. So in many cases, it's okay to take beta as same as like 1.4192, 1.42. It's okay to take it like that. So this optimization that we have done for array, this is kind of, it doesn't give us that much valuable information in addition to what we already know, that the optimum value of beta is this much, 1.419. Okay, now we'll do one more thing. So this is again trying to find out a Z optimum for natural convection. So between fins, there's a Z, right? So if there's a channel, this is the Z, this is the interfin spacing, which in the case of array, we are saying the spacing between fins, right? So that is that Z. Now let's look at optimum single fin heat transfer. We know it's this much. What is 2h kt to the power half? This is same as square root of hp kac, right? And then we had theta b, and of course tan hyperbolic beta. This is the single fin heat transfer. Now there is some work which was done by a gentleman called Alan Bucks. This is a very old paper. So he said that H optimum multiplied by Z optimum divided by K of the fluid, which is the optimum Nusselt number, is 1.25. So this is from an analysis which we will not have the time to cover. We are just saying that, just taking it like that. And this gives you H optimum as 1.25, K fluid divided by Z optimum, just writing from here. Okay. Now let's say we look at the total heat transfer from the fin array. Now the fin array consists of these fins. Now the fins have been optimized. Single fin has been optimized. What about the heat transfer from the interfin area? So the interfin area will depend on, that interfin heat transfer will depend on a Z optimum. Suppose we take the Z optimum based on this, based on what Alan Bucks had said. Then the total heat transfer is a single fin, just a fin heat transfer plus the heat transfer from the interfin area, and we get an expression like this. Now let's try to see, first of all, let's try to see this quantity. Okay, so this one is this is a fin heat transfer. So that is QSF. All right. QSF by L. So QSF is root PK, root HPKAC theta B and hyperbolic beta. Beta is in B. This is your familiar expression when we have an insulated tip. Right? Now, this thing is H2L A and T. They see. Remember, theta B is not within the square root. Okay. So this is theta B tan hyperbolic beta. Okay. So QSF by L which is what I have here, QSF by L, that will be, just look at this, 2H K T to the power half. Instead of T, now I write at this step, I write a T naught. Okay, what is T naught? This is the optimized value. Now this is theta B. What should I write for tan hyperbolic beta? Tan hyperbolic beta, for that, what's the value that I should write? Tan hyperbolic 1.4192, because I'm going to the optimum thing, right? So I'm saying that we have this array and the fin is actually an optimum fin. Right? All right. So this is 1.4192. Can your calculator do this term? You should know these things because in examination also you might have to do tan hyperbolic, cos hyperbolic, sin hyperbolic, things like that. 0.889. The next digit? 431. So 0.8894 is okay, right? So this is 0.8894. Now we also have from here, we have a root 2. Okay. So that root 2, let me write that here. This root 2. And we have HK T naught to the power half, correct? Now what is root 2 multiplied by 0.8894? 1.25, do we get 258? 1.258. All right, so that explains that 1.258 in this expression. So this is 1.258 and okay, there's a theta b, this also has a theta b. So 1.258 theta b, and then we will write this, okay, in terms of AP. So in terms of AP, it can be written as h square AP k to the power 1/3. Which is what that expression where the pointer is like, okay? So this thing is the same as this. It requires slight bit of work, so that part of the work I will do now. Let's see. All right, now h square AP k to the power 1/3, right? So what is it? This is h square one-third. AP is BT, and Okay. How do I get this from here to here? So for that, beta is 2h by kt b. Do you agree with this? Yeah, beta is mb and m is just this one. So this is easy. And this means beta squared is 2h by kt b squared. So T by B is 2HB by K beta square. Now let's see what is 2 over beta squared. Beta is 1.4192. Okay, so what is this 2 over beta squared? 2 over beta squared is 2 over 1.4192 squared. So this is how much? Yeah, so I had written it somewhere. 0.9928 or something, right? Yeah. I think I've written it here. Okay, to be precise, 0.992985. Okay, so it's kind of like 1. It's not 0.997, that would have been better. But okay, this can be taken to be 1, not a big problem. So this is kind of like 1. So this is approximately HB over K. T by B is HB over K. And going back to what we were doing, is this okay? This one from here, is it okay? What is KT by H? From here, KT by H is B square. After making this approximation, KT by H is B square. We got this. And square root of KT by H is, this is B. This part is B. Then we also, this is that B. And KT is just written like that. Okay. Now this tells you this is H squared KT to the power 3 by 2 and no, not H squared. Actually, this is H to the power 3 by 2, correct? Because we have an H square and we have H to the power half, so H to the power 3 by 2. This is KT to the power 3 by 2, and this whole thing to the power 1 by 3, which is HKT to the power half. Okay, so this requires a little bit of work. So that's why I did it on the board. The book directly writes it. So this is important. It actually has this approximation built in. And based on that, we can get QSF by L as 1.258 theta B H squared APK to the power 1 by 3. So I've kind of done it the reverse. in the first expression, it's 2hkt to the power half. So hkt to the power half, I've done the reverse way. You can also take hkt to the power half and show that equal to this. But this is a bit easier. So I went like, okay. So what have we got now? We have got this term for the fence. Okay. But this is from the book. This I've taken from the book. I realize that there is a mistake. What is the mistake? Power should be 1 by 3. Now, this is a nice book, the book by Lee that we are following, but there are errors like this. So that's why this is important to check everything. Yeah. So initially, I also thought that okay, I mean, sometimes I don't check every single step, and with this book, I had some difficulties. When I didn't check every single step, I got into trouble. Okay, so this is one example. So this I checked. This should be 1 over 3. Okay, the book says, actually the book, somewhere it says half, somewhere it says 3 by 2 and all that. But in spirit, we understand that what we have done is we have taken the single fin heat transfer and written it in terms of AP after making some approximation, right? Slight bit of approximation. So it's written in terms of AP. Then this term comes for the interfin area. Okay. Then we can get a Q total by this thing with some work after this from here. By the way, what is this term? This is N. This is the number of N's. This is W divided by Z plus T. This we get. Right. So Q total divided by L W theta B. What are L and W? L and W will show up from this one, L and W. This is the primary surface area, full area on which you're placing this fin array. So with little bit of work, this can be shown, okay, starting from the previous expression. So this has got a 1.25 K fluid and all that. Where does this 1.25 come from? It comes from Ehrenbass's expression. Ehrenbass's expression gave something for H optimum, which is for that interfin area. Okay, and that's why that 1.25 came into picture. We have also in the expression here in the denominators, we've also used this thing. Now, is this familiar? This we had done for the optimum Z when we had natural convection. So this is like small spacing channel, large spacing channel. Then you equate the two, and then we can write. We could write it in terms of an expression given by Rosenau, which gives you 2.714. All right. In case you are wondering where it came from, we had seen this some time back. Yeah, it's this thing. Okay. Now let me explain one thing to you, that sometimes these sort of expressions will look ugly to you. In fact, why sometimes, most of the times you'll find it ugly. But just think about it from my point of view. If I start deriving every step, then it will become rather tedious for all of you. So I am not doing that. Okay, so I'm just directly representing the final expression. And what I'm saying is, two things. One, you should know how it has been obtained, which I think I've already explained to you. And the second thing is that the real numbers are not very important, because whenever you want to use this expression, you can go to the book and pick up this expression, right? So it just, the only thing that you need to know is that LN-mass has been used here, and that small spacing Z optimum has also been used. So we have got this, where we have taken care of both the fin heat transfer as well as the interfin heat transfer, right? Okay, and there's some more approximations which are possible here, where the heat transfer from the interfin area, if that is neglected, then we can get an expression like this. So I'll not discuss this one immediately, but from here to here, heat transfer from interfin area, if we neglect, then we get this. All right. Now this gives you sufficient background for fin arrays. Whatever is not clear, those will become more clear if we do some problems, and for that we have tomorrow's class as well as some work that you can do at home, which you should do at home, fin array. Now, before we proceed further, let me also show you some figure. This is a figure from an old book. So there's a book by Krauss and Barkohen. This is in fact freely available. It's called the Design of Heat Sinks, I think. It's there's a website called archive.org. Archive.org, you know that. Some old books are scanned and kept there also. So you can find this book there. And this gives you a nice enough representation. It says artist's conception. So just some figure, somebody who has sketched this. But this is kind of, I like this because this shows that this is an electronic circuit. There's got various electronic components. There's a capacitor, I believe. And on the back side of it, we have the fin array. The difference between what we have done till now and this one is that this also has a plate here. You know, in some cases that we considered, we didn't have a plate which is closing the fin tip. So this is slightly different, but good to be able to visualize all these. And this one I had shown you. So this is a different arrangement where the fins are going up vertically, right? Here the fins are jutting out in the horizontal direction, but we call this vertical fins in fact, right? So we have this. So this I had shown you that, okay, there is some chip and then there is a heat sink bond. So some bonding material which bonds the heat sink to this arrangement. Then there is a flow and then there's heat transfer taking place. Right? So this is some analysis that we have done. In the next few minutes, we can also look at some possible scenarios that we will encounter in electronic cooling. So this is for this there is no book. I couldn't really locate a proper book for this, but this is a lecture which I got on YouTube. This is a lecture by an IIT Bombay faculty member. His name is Shankar Krishnan. I acknowledged the source at the bottom. So I forget the title of the lecture, but maybe you can say cooling, electronics cooling, Shankar Krishnan, IIT Bombay, then maybe you can find this lecture. So he had some visuals which I'm sharing with you. So this is like, this is a fin array. So this is now this fins are going up like this, right? So that means the electronic circuit will be here, the chips are here. Then you have these fins. So this is a fin array. And there is some, so this is a box kind of thing. So this is another surface, maybe another circuit board coming on top of this, or something else coming on top of it at the tip itself, right? So there is no gap. So this he is calling a simple arrangement. Now there are other arrangements also possible. So here you see that the tips are not closed by another surface. Here you got some gap, right? So this is a simple arrangement, this is a moderate arrangement, this is called a complex arrangement. So what is a complex arrangement? In case of complex arrangement, you can see that there is a, okay, in case of, first let's go to the moderate arrangement. Moderate arrangement, there will be some bypass on the top, right? So imagine flow going, imagine flow coming in this direction. So some flow will go through the fin array, but some flow might bypass the fin array and go from the top. In fact, the upper part gives you less flow resistance, so it will tend to have flow in that significantly. Whereas in this case, the flow has to go through the fins, right? So why do we do these various possible arrangements? Actually, it's not always in our hands, because electronic circuitry is such, because of space considerations, because of how different components have to be placed. Maybe you'll end up with one of these arrangements in your setup, or maybe more than one of these arrangements in what you are doing, right? So if there is a moderate arrangement, we can see that the flow can go through the top. Of course, it will go through the fin array also, but there will be bypass, right? This is a bypass flow situation. But in this case, there is no bypass as such. And why is this complex? This is complex because there is a tip clearance. It says tip clearance and side bypass. So there is a clearance at the tip, like in the moderate case also, but flow will go through that clearance zone. But in this case, the flow will go from sides also, right? So these are things which designer has to be conscious about. All right. So this is heat sink thermal resistance as a function of number of fins. Again, I've taken from Professor Shankar Krishnan's presentation. So there's a YouTube video, and what I did was actually pause the video and grabbed some figures from there and pasted in my PPT. Okay. So if you have flow bypass, basically the thermal resistance can go up. The fin heat sink thermal resistance can go up. And this is without flow bypass, it kind of goes like this. Now for these arrays, we will also talk about thermal resistance and fin overall surface efficiency. This I think we can do kind of quickly because you already know this. So we are talking about a fin array. What about thermal resistance? What about the thermal resistance of fin array? I had actually shown some resistances in one of the figures, but we have not talked about resistances here. So what is this? This is like it's kind of an arrangement like this, of course, fin array. And for such a fin array, you again have this is QF as single fin efficiency multiplied by HAF theta B. You know this from undergraduate days. H times AF is the fin area, theta B is TB minus T infinity. So the heat transfer resistance of a single fin. So we'll go to the heat transfer resistance of a single fin, then we'll go to the heat transfer resistance of the fin array. So for a single fin, it is theta B by QF as expected. And using this, theta B by QF is this, right? And this is for a single fin. Now, overall inefficiency of the array is Q total by Q max, and you use an overall efficiency to write this. Q total is eta O H AT theta B. Correct? So that's understandable because for a single fin, you had eta F for fin array, you use eta O, right? And then Q total. Just have a look at this Q total and tell me whether this you can follow or not. This is A total. A total is N, the number, multiplied by A of the fins plus A of the intermediate space. So that's given by this, and Q total should go like this. So we don't have much time now, but I'm sure you've seen this in undergraduate, right? So just take 1 or 2 minutes. We have 1 or 2 minutes, and tell me whether this seems reasonable or not. Whether you can work this out or not. You don't have to understand everything. Overall, does it kind of look all right? You have seen this in an undergraduate or not? Connecting the overall efficiency of a fin array to the individual fin efficiency. You've seen this, right? It's there in undergraduate textbooks. This should be all right. In case there is any difficulty, let me know. I will address this in the next class. Okay. So we now understand something about thermal resistance of the array as well as the overall efficiency. And we'll take this up little further on Friday. Now there's no time.